so before we talk about what we're actually going to talk about today, page 24, the third page of notes, we're going to do what I call confessions of a bad teacher. Because I had already just figured that I have to do this for the back of this page, but yesterday as I was sitting there after school and I was like printing out the key to the homework and stuff, I was thinking about something we wrote and I thought, why did I write it that way? And then I started second guessing everything and I was like, no, I was just wrong and I don't know why I did it. So let's look at, we don't have to rewrite everything. It's not that big of a deal. So, I mean, it's a big deal, but it's not that big of a change. This is the very bottom of the front of that piece of paper, right, where we talked about the secant line. Okay. And it says P is concave up, so the secant line is above the curve on the closed interval from 2 to 4. All right, so the closed interval from 2 to 4, that is what we used, even though it wasn't written that way, that was what we used to find our average rate of change, right? Okay? That it is closed because I used 2 and I used 4. You with me? All right, so now here, is that secant line above the curve on the closed interval from 2 to 4? Where is the line at 2 and 4? Isn't it on the curve? So at 2 and 4, the line and the curve are in the same place. Between 2 and 4, it's above the curve, and on the outside of 2 and 4, it's below the curve, right? So closed interval here does not make any sense because it's not above the curve on all of that because of the 2 and the 4. So this really just needs to be an open interval, and I want to make sure that you understand why. Does that make sense? Because at 2 and 4, I'm on the curve. So just change it to parentheses. And I can't believe I went all day just thinking that that was a great idea. But I think I was so focused on making sure you understood the picture, and I even made a big deal about you have to say these things, and if you didn't say this, you didn't get credit. Well, if you said it the way I did, you wouldn't get credit. But with the open intervals, you're good. Okay? Everybody okay on that? All right, so now flip it over because we got more. I'm pretty sure this is the flip chart I saved for this, this classes, so I'm pretty sure this is exactly what we wrote in this class, because I also messed it up 5th period, but somebody called me out 5th period at the end of the class, but at least they did it. So on number 1 here, do you have written F is quadratic because average rates of change of F are constant over equal length inputs? Okay? Yeah. All right, so let's think about that, what we actually wrote here. It says F is quadratic because average rates of change, that's this column right here, are constant over equal length inputs. No. If the average rates of change are constant, that makes it linear, and they're clearly not, right? It's the average rates of change are changing at a constant rate. This is the average rate of change of the average rate of change. So here's how we can fix this without making it too terribly bad. F is quadratic because average rates of change of F are changing. See, we have room over here. At a, we're going to mark out R, constant rate over equal length inputs. I think I was so focused on that part. It was the end of 5th period, somebody said, come here, this is what we wrote. I was like, yeah, that's not right. He was like, well, that's what you did. I was like, oh my God, it is? And I was like, oh, I did it right in 2nd period. And then I don't know what happened in this class, but anyway. Does that make sense why I have to say that? The average rates of change are changing at a constant rate. The rate at which they're changing is constant, not the rate itself. Everybody okay with that? Now, clearly I've messed up so much that I have a name for it, the confessions of a bad teacher, but it doesn't happen every single day or every single week. But this is why if I say something that seems weird, you need to call me out on it, all right? Or if you're like, I think that's right. Maybe you're right. Maybe I'm wrong. And I don't know why I wrote it that way. But are we all good now? Did I totally confuse anybody? We're okay? All right, good. I apologize for that. All right, so then grab your notes for today. You can put that away. And this is going on page 25 when we're done. All right, this one is titled Polynomial Functions and Rates of Change. Polynomial functions, we've heard those words before, right? Okay, so I know you have. You've done things with polynomials. You've factored them, you've graphed them, you've done all kinds of things with them. I don't know, however, if you have actually seen the official representation of a polynomial function right here, right? And here's rule number 1 in here always. No matter what I show you or say to you, rule number 1 is don't freak out. Because as soon as you freak out, you're like, what the heck is that? Then your brain shuts down and nothing else matters. So yeah, that looks all crazy. Are you going to have to rewrite that ever? No. Do I want you to kind of understand what it's saying? Absolutely. But if I never show you stuff like this, and you get to a class in college where you're kind of teaching your math or science yourself out of a textbook, because that could totally happen, and this stuff like this freaks you out and you think you've never seen it before, then I'm not really doing my job. So polynomials are old news for you, and so you really do know what is happening here. I'm going to simplify this a little bit by giving you another function. So we're going to say we have h of x. And h of x is going to be 5x cubed plus 4x squared minus 7. Okay? That's a polynomial. Multiple, poly meaning many, nomial meaning like terms, basically. So what all this says is this. If I start with this first term here, and it's x to the nth power, then the next one is n minus 1. So since this is to the third, my first one's to the third, 3 minus 1 is to the second power, right? Then this would mean I should have an x to the first power, which I don't, but I kind of do. If I wanted to write it out in that form, I could add right here, I can add a plus 0x term. We just don't do that, right? Sometimes we do. When we do like long division, we got to add stuff like that in there. But so there really technically is one. Okay. And then you have the a, all of these are your coefficients. And then, I mean, we could have, x to the thousandth power. So we don't know how many there are, but it finally gets down to x squared, then x, and then just a constant. So that's all it's saying. We have to, in math, have something to represent every polynomial. And so sometimes the notation gets a little weird when you want it to apply to everything. Okay. But I want you to see it. Nobody's going to ask you to rewrite it or anything, but we should be able to at least answer these questions down here after we talk about this. N is always a positive integer. N can't be negative because then that puts a variable in the denominator and it's no longer a polynomial. A sub I, meaning any of the A's, A is a real number, so no imaginary numbers as coefficients, and A sub N is non-zero. So basically, I could, if I did have I can add the plus 0x. Everybody understand why I can do that? What I'm not going to do is put a 0x to the fourth first so that I can say it's a fourth degree polynomial. Like the very first coefficient can't be 0 because that doesn't make any sense. That's all that means there. So my leading term in general for a polynomial, these are my terms, and this is my leading term. So it is a sub n times x to the nth power. The degree is n of the leading term. Now, this generic one here is in standard form, meaning that the largest power is first. Sorry, let me preface today by this little, probably maybe TMI, or it's not too much information, probably just don't really care, but I have bouts of insomnia, and it came back last night. It makes my mornings very, very bad, and so I've had very little sleep. And so I've been having trouble grabbing the words out of my brain. So especially today, if I say something weird or I need to repeat it, or you're saying, oh, whatever, let me know, because my brain is not firing on all cylinders right now. All right, so the degree, so if they're not in order, just make sure the highest exponent, that is your leading term, that would be your degree. And then your coefficient, that word is not new to you either. Those are the numbers in front of your variables, and so the leading one would just be a sub n. Okay? Everybody okay with that? Any questions? All right. So this says to find the leading coefficient. These hopefully are pretty easy questions, but we're going to add a little stuff to this. So it says find the leading coefficient and degree of the following polynomial functions. So this is my leading term. The whole thing is my leading term because x to the fourth, that is the highest exponent I have. So my leading coefficient is the number, which is 3, and the degree is 4. Okay? Now, we're going to talk about even and odd degree polynomials. We're also going to talk about even and odd functions. And even and odd functions should be something that you discussed in Algebra 2. We're not to that yet. We're just talking about the degree of the polynomial itself. So this is a 4th degree polynomial. 4 is an even number. That makes it an even degree polynomial. Make sense? It's really easy to figure out if it's even or odd, as long as you know the difference between even and odd. And we're also going to talk a lot about something called end behavior. So we're going to talk about it a little bit today. It's pretty easy to kind of wrap your mind around and just know it's going to be coming back a lot. We'll officially define things or whatever. Now, I don't know, without plotting some points or using my calculator or something, exactly what that's going to look like. Okay? And that's fine. But there are some things that I know. Because it is an even degree polynomial, the end behavior, meaning where the arrows go, okay, it's going to model a quadratic. If it was odd, it would model a cubic. So here's what I mean by that. And you don't have to draw this because we're going to draw some of them. I'm just going to give you a general overview first. So that's even, and it was positive. So this is what a quadratic looks like, right? When the leading coefficient is positive. If I have an even degree polynomial, and it has a positive leading coefficient, then I don't know necessarily what's going on in here right now, but I know the ends are going to match the ends right here. Okay, you with me on that? It's going to be up, up, and I'm going to show you why here in just a second. And then this is what a cubic looks like, right? So if I have an odd degree, then it's going to start down here, who knows what's going on, and then it's going to end up here where the ends are going to be opposite from each other. No matter what the degree is 27. 27 is an odd number. I know that the ends are going to point in opposite directions. 1,000 is an even number. So I know the ends are going to point in the same direction. You with me on that? Okay. Because that's going to be very helpful to kind of wrap your mind around some things. All right. Let's go back over here then. So here's what I know. If I have a quadratic, I have at most how many x-intercepts? 2. That's the most I can have, right? Is it possible to have 1? Right? It's possible to have 1. Let's go back over here. So if I have 2 intercepts, it looks like this. If I have 1, it looks like this, right? If I have none, it looks like that, right? But the most I could have is 2. Can't have any more than 2. And if I'm just looking at this equation, we don't need to know right now exactly how many zeros I have for sure, just what is the maximum that I can have. Since this is a 4th degree, I'm going to have at most 4 x-intercepts. You with me? All right. So we're going to sketch something that is probably not going to look anything like what the actual thing would be if we graphed it on our calculator, but it's going to give us the information that we need. Okay? So I know that it is even. So I know that the end behavior models the quadratic, which means it would be up, up for a positive quadratic. So I'm going to start up here. I need 4 zeros. So I'm going to go through 1, go back up 2, 3, 4, and then here are my 4 possible zeros. And you notice it's up, up like that. Okay, we okay with that? Now, one of the things we're going to look at, because we're going to talk about some other terminology, but this terminology is used sometimes, so I want to at least bring it up. Because I start here, my function is decreasing till it gets to here, then it's increasing to here, and then it's decreasing to here, right? Now remember, I have at most 4 x-intercepts. I could have less, so I could have less of those little green dots, but at most, I'm going to have 3 of those, and one of the terms that we use for those are turning points. Because I was decreasing, then I turned, and I increased, and then I turned, and then I decreased, okay? So turning points. So because my degree is 4, I have I have up to 3 turning points. I don't know if I just said at least. It's not at least. I have up to 4 x-intercepts. I have up to 3 turning points. Okay. Everybody good with that? The maximum number of turning points is the degree minus 1, right? Not that hard. And again, if you're not sure, think about how many zeros you could possibly have, sketch something out, and you can count them. I mean, that's why I'm showing you those kinds of things. All right, so now let's look at B. What do you think the leading coefficient is here? -7, because this is the leading term, even though it's not in the front, because that has the highest exponent. So my leading coefficient is -7, and my degree is what? 3. Okay, so we're going to draw a little function here. Now, this is what the parent function of a cubic looks like. That's y equals x cubed. My leading coefficient is 7, which means it flips it, right? So instead of starting down and ending up, I'm going to start up and end down because of that negative. We okay with that? That's what that negative does. And because this is cubic, and I have a few cubic examples on here, and so at the end of last period, somebody asked, is this always for cubics? Yes, but it could be the 5th degree, the 7th degree, whatever. I just didn't want these to be huge exponents because then it was hard to draw the little thing. But it's not just for cubics. It's for any odd function. So I'm going to start up here, and I have 1, 2, 3, up to 3 x-intercepts, right? So since I have up to 3 x-intercepts, that gives me up to 2 of the turning points. Okay. So I have up to 2 turning points. Any questions at this point? Now, we have, so the arrows are our end behavior, and that's the part that's modeling them. The stuff that's in the middle is all different, but that's just kind of a preload of some things. Are we all good on that? Somebody wake her up. She's missing all the fun. All right, what about C? What do you think about the, leading coefficient? What do you think it is? What's the only number you see? 4. Is a 4. Then the degree, what do you think? 1? Okay, so if it's 1, it would look like this, because that'd be x to the first power, right? There's nothing there, which means this is actually x to the 0 power, because anything to the 0 power is 1, right? And that'd be 4 times 1, so my degree is 0. If I did have a first degree polynomial, that would be a line. What does this thing graph? A line, right? What kind of line? Horizontal or vertical? Horizontal, very good. So this is what it would look like. So do I have any turning points? No. I'm not increasing or decreasing anywhere, so I'm definitely not changing. Like the whole thing is just constant, so I just have no turning points. Everybody okay with that? All right, good. All right, so now we're going to talk about extrema. Extrema is the plural. Or what word do you think? Extreme, yeah. So extremes is plural, extrema is plural, kind of means the same thing. It just sounds fancier. So extrema. The extrema of a graph are the minimums and the maximums of a function, which I know the concept is not brand new to you, and we've actually even found one in the calculator already, but here's where we're going to actually define stuff. There are 2 types of extrema. 4 names, but 2 basic types. The first one is relative or local extrema. So I could call it a relative maximum, or I could call it a local maximum, and they mean the same thing. You could be asked or given that information in both ways, so we just have to know that there's more than one way to say it. So a polynomial, and we're only talking polynomials here, has a relative minimum or maximum where it switches between decreasing and increasing. Here's an extra little tidbit of information. Or at an endpoint if the polynomial has a restricted domain. So when we look at this right here, is this, or does this function right here have a restricted domain? It does, right? Because it's not all real numbers. It's not negative infinity to infinity. I start here at -4, and then I would go all the way to infinity. All right, so I have a restricted domain, which means this guy right here, he is in play. Okay, so my local maximums, or my local minimums is what it is first. This is a minimum. Okay, it can be an endpoint. Then I increase, that would be a maximum, and then I decrease, that would be a minimum. Then I increase, and then this goes all the way down to negative infinity. Okay? We have two ways we're going to talk about maximums and minimums, what their values are and where they are. So when I look at this point here, the local minimum value is -3, but it is at -4. Okay, and again, you kind of could be asked both, but it's at -4 because at is going to be the x value. So we have one at -4. We have one at 0. But this guy, negative infinity is not a number. So even though my y's decrease until we get to negative infinity for a y value, I do not count that as a minimum because, again, infinity is not a number. Okay? We okay with that? All right. So then we have the maximums. From here, I'm increasing, boom, maximum. Then I decrease, that's a minimum. I increase, maximum, and then I decrease. So I have two local or relative maximums. They would be at -2 and at 3. Okay, everybody okay with that? Perfect. Any questions? All right, so your relative or your local, it's in the little neighborhood. In this neighborhood right here, he's the maximum. In this neighborhood right here, he's the maximum, right? That's the way it's just in that little kind of neighborhood. That's what makes it the local or the relative. Just local, like a local neighborhood. All right, so then we have absolute or global. So this says of all local maxima. So all of them are local or relative. Then you take a local or relative, and then they get another more special name. Okay, so they fit, if it's absolute or global, it actually fits in both categories. This is just a better answer for it. It is the greatest or the least of all of the maximums or minimums. Okay, so when we look at this one, so when I look at my maximums, I feel like the highest value would be right there, right? The maximum, the largest y value there is at that point. So the absolute maximum value is 2, and that occurs at 3. Okay? The value is the y value. The location is the x value. We all good about that? Any questions? All right. So my minimums, my options were this and this. But remember, it has to be the least of all of the numbers. This is going to go all the way to negative infinity. So the smallest y value is not either one of these. The smallest y value is actually negative infinity, which is not even a value. So my answer is none. Okay. Y'all okay with that? Any questions? All right. So flip this over. And I'm going to give you a second to answer A. Then we're going to talk about it. Okay, so I have a random name picker, but because I am videoing this, I don't like to put your names up on the board, and I didn't even think about pulling it up on my iPad until right when class started and I didn't have time. So I'm going to try to be random. I'm not really good at randomly calling, but I'm going to get some people to help me out here. And I'm going to try and mark you off so I don't ask you more than once. All right, so Grace. Let's have Grace start with me. Relative minimum, where? Is there one? No, okay. Oh, and I forgot, it does say right in A. I meant to change that to none. I like none better. It doesn't really matter. So there is none. Not a trick question, I promise. Alrighty, on relative maximum, where? At 1, x equals 1. Y'all agree with that? Are there any more? No. Okay. Absolute minimum value, Barbara? None. Good, because they're going to negative infinity, right? So this is none. And Angelise, absolute maximum value is what? 3. Good. Where? 1. Everybody good with that? Okay. So I'm going to do the same kind of thing for the next ones, but I'm not going to give you time to think first. And that's okay. So when I call on you, you need a second to think. Totally fine, because you didn't already do it. All right? And if we need to think through it together, we can. Not a problem at all. All right. So on this one right here, relative minimum, Adam, -2. Is that it? Yeah? Okay. You all agree with that? Yes? Okay. Relative maximum, Logan. -4 and 3. Y'all agree with that? Anything else? All right. Good job. All right. Daniela, absolute minimum value. -3 at -2. Do y'all agree with that? Yes or no? No? We have some disagreement. Why? Who wants to disagree? In a kind way. Logan, what you got? None? Why? Because the arrow. So this totally is a relative minimum, but this keeps going to negative infinity, which means we're not going to have an absolute minimum. Does that make sense? Okay, good job. Thank you for answering. Totally okay to not always have everything 100% right, so I'm just going to mark those out and put none. Because that is a very common mistake there for sure. Alrighty. Julian, absolute maximum value. 2, where? 3. Y'all agree with that? Yes? Okay, good deal. Alrighty. Mario, relative minimums on this one. -3 and what? 0? So -3 and 0? Y'all agree with that? He's questioning himself now. I saw the look on his face. -3 and 3. Good. I wasn't sure if you were trying to give me the y value there or what was going on there. But all right, good job. Thank you. All righty. Victoria Prado, relative maximums at what? 5. Okay. Do y'all agree with that? Yes. Very good. Don't forget the endpoints. Absolute minimums. Ileana. All right, absolute minimum value. What would that be? -3. Good. Where? -3. Good. All right. Then Mary Angel. Absolute maximum. 4 at what? 5. Good. Any questions at all? We all good? Yes? The concept shouldn't be brand new, right? Put the pink paper away, please. That's not what you should be working on right now. All right, so fun facts. Not only are these fun facts, they're facts we need to know. So it's fine that they can be fun too, right? If I have, says between two real zeros of a polynomial, there must be at least one local maximum or local minimum. Okay. So let's think about that. Why, right? If I look here, okay, here are two real zeros. So if I come up through the x-axis here, and then I got to go back down through here, I'm going to have a relative maximum of some sort, right? Or if I go down, for me to be able to come back up, there's going to have to be a relative minimum. So you have to have, that's kind of how we knew how many turning points there was and whatnot. And then here's the next part of that. Polynomials of even degree must have either a global maximum or a global minimum. Okay, and that I have for sure seen with some multiple choice questions. And so we're going to talk about why that is what it is and how you are going to know what's going on. So we're going to write down here. I tried to give you some space down here. Whatever you have is plenty. I'm going to pose the question, global maximum question mark, okay? Basically, does the function, I didn't have to write out a ton of words. Does the function I'm about to give you have a global maximum, right? And then this, so I have, if I give you g of x equals 4x cubed plus x squared minus 2. Okay? Now, this statement only talks about the even degree polynomials. It doesn't talk about the odd, right? So with the odd, let's think about what's going to happen here. If, and again, this is a cubic. I could have given it to you through the fifth or whatever, but I'm going to have, it's going to model the end behavior of a parent function of a cubic. So that means that whatever this is, and I have, at most 3 intercepts, it would look something like that, right? So because the end behavior is going to model a cubic, whether that's x to the 5th, x to the 7th, x to the 35th, whatever, the ends are going to be going in opposite directions. That means one side's pointing to infinity when the other side's pointing to negative infinity, and it really doesn't matter which is which because there's no way I can have a global maximum or minimum. You with me on that? So then, so this really should say polynomials of even degree must have and odd degree won't have, but here's what we can write here. And we can just say, no, this is an odd degree polynomial. Okay. Then I'm going to give you a different one, g of x. Let's say g of x is equal to 2x to the 5th minus 6x to the 6th plus 3. Okay. What is the degree of this polynomial? The 6th, right? Because it's not in the right order, so this is actually my leading term. This is an even polynomial, even degree polynomial. So I can't just automatically say no. I also can't say automatically yes, because the question is, do we have a global maximum, not do we have a global maximum or a minimum. So I know I should have one of them. This has a negative leading coefficient. If a quadratic has a negative leading coefficient, tell me something about it. What happens? It opens how? Down. So for a quadratic, it's going to look like this, right? So if I wanted to draw this, I could do something like this. I would have up to 6 intercepts, but so 1, 2, 3, 4, 5, 6. So it's going to be down, down. even without drawing this, I know that it's going to be down, down. I really don't care about the middle stuff. So because it is down, down, that means I have to have a global maximum, right? I could have at most 3 global or 3 relative maximums, but I have to have one like that. So then my answer is going to be yes, global max, because G is even degree polynomial with negative, so I can abbreviate negative as neg, leading coefficient, and I can abbreviate coefficient also. Good thing, because I'd probably spell it wrong. All right. I know you're still writing, but what questions do you have at this point? Anything? All right, so then you can go ahead and tape this in. I'm going to give you your assignment.